Hello all. Today's topology seminar, Beckham Myers from Einstein Institute of Mathematics is joining us. So he will present categorification and homotopy theory. So Beckham, please.
Thank you, Cihan. Thank you for the opportunity to speak today. My goal broadly will be to try to tell a story about how categorification will very naturally lead to some of the ideas that lie behind stable homotopy and chromatic homotopy theory. So my goal is that everybody here should get something out of the talk. So to that end, please feel free to ask questions or to interrupt at any moment. So I want to start by talking about categorification. And I think categorification is best illustrated through examples. So to that end, I want to speak about a few examples. So if we can imagine, for example, that I have some apples and you have some pears, and we want to exchange them. Well, the first thing we might do to ensure that there is a fair trade is to line up the apples with the pears to associate every apple a pear. And then at some point in history, somebody realized that, well, instead of actually lining up all the apples with the pears, well, we can denote such a group of apples by the number 3, by the symbol 3, whenever there exists some such bijection between a set of apples and any set with 3 elements. And then the statement that there exists some bijection between my apples and your pears can be expressed by the equality 3 equals 3. And this is like perhaps the first example of what we can call decategorification. So let's denote by fin simply the category of finite sets and all functions between them. And I'll say that fin is a categorification of the natural numbers. So to illustrate, well, there are familiar operations that you can do with natural numbers. For example, the sum of 2 natural numbers corresponds to the disjoint union of 2 finite sets. The product of natural numbers corresponds to the Cartesian product of sets, and so on. And even various equalities that relate these operations. For example, the fact that the product distributes over the sum. Well, these correspond to natural bijections between various operations you can perform on sets. So in this case, the distributivity of multiplication over addition, it's witnessed by the existence of this natural bijection between, this Cartesian product and this disjoint union. So another illustrative example comes from representation theory. If we consider, let's say, a finite group G, well, for every G representation, V, we can form its character. And in this setting, well, operations you can do with characters. For example, you can take like the pointwise sum of 2 characters. Well, they correspond to operations in representation theory, the direct sum of 2 G representations, for example. Or you could take the product of 2 characters, and that corresponds to the tensor product of representations. Or say, if you're working over the complex numbers, then, the complex conjugate of the character will correspond to the dual representation. So in this sense, I'll say that character theory is a decategorification of representation theory. For our third example, we can consider symmetric monodal category. So symmetric monodal category is just a category C, which is equipped with a unital, associative, and a commutative tensor product. So it's a function from C times C into C. And it needs to be associative, which in this case means that there exists a natural isomorphism of functors, which witnesses associativity of the tensor product. And similarly, there is an isomorphism of functors, which encodes commutativity. So for example, the category of vector spaces over the complex numbers is a symmetric monodal category with respect to the usual tensor product of vector spaces. And now it's important that we're taking this associativity to be encoded in a natural isomorphism of functors. It's not true that the tensor product of vector spaces is strictly associative or strictly commutative, but there exists natural, like the obvious bijections. And in general, part of part of the data of a symmetric monodal category is these natural isomorphisms which exhibit associativity and commutativity. So another example is, say, supervector spaces. So supervector spaces, and the underlying category is given by like Z2 graded vector spaces. But now, like the natural isomorphism which witnesses commutativity is non-trivial. So in this case, I'll say that a symmetric monodal category should be considered as a categorification of the notion of a commutative ring. So that means operations you can do in a commutative ring, like taking the sum of two elements, correspond to, for example, the direct sum of two objects in the category. The product of two elements correspond to the tensor product of the two objects. And there's even more like exotic operations you could do. For example, you can consider the exponential of an object, and it corresponds to the symmetric algebra on an object in a symmetric monodal category. So this is, for example, if you're working in a ring in which you can take denominators, because, well, x of x is given by this formal power series. And the symmetric algebra on an object, well, it's given by the following formula. You take the object to the nth tensor power, and then you quotient out by the action of sigma n, which acts by permuting the coordinates here. And then you sum all of them together. And this construction, well, it generalizes the symmetric algebra on a vector space, for example. But also, if you apply it to, say, supervector spaces, well, it simultaneously generalizes the symmetric algebra as well as the alternating algebra on a vector space. And the point is that, well, in the categorified setting, you don't have to worry about some almost technical details which appear when you work in the uncategorified setting. So for example, if you're in a commutative ring, then you have to talk about questions like convergence of this power series. But in a symmetric monodal category, this the expression always makes sense. So that's also a theme that when you categorify, some of the technical conditions or finiteness conditions or convergence conditions fall away. So at this point, we have three examples to consider. We have finite sets as a categorification of the natural numbers, G representations as a categorification of G characters, and symmetric monodal categories as a categorification of commutative semi-ring. So a semi-ring is a ring in which you can add elements, but there don't exist necessarily additive inverses. So maybe I'll pause right here if there are any questions. Okay, in that case, so I want to make in light of these examples two remarks. So the first remark is that in all of these instances, the process of decategorification is pretty simple. It's pretty systematic. We simply pass to the isomorphism classes of objects. So isomorphism classes of finite sets are determined by their cardinality. And similarly, G representations, let's say we work away from the order of the group, are determined by G characters. And from a symmetric monodal category, you can obtain a semi-ring just by taking the isomorphism classes of objects. But the other direction, the process by which one categorifies, is much more subtle. It's like not clear how, if you start with the natural numbers, you might end up thinking about finite sets. Or even more so, if you start with a G character, how you might realize that you should interpret a G character as coming from like traces of a group acting on a vector space. But so this is where the creativity and the ingenuity lies in properly categorifying. But roughly, we could say that categorification is about replacing equality with equivalence or structure. So that's the first remark I wanted to make. And the second remark is that, well, in all of these above examples, there appear a good notion of subtraction after decategorification. So for example, if you want to formally allow subtraction, then you're led to consider the integers from the natural numbers, or virtual G characters and commutative rings, where now it's possible to subtract elements from each other. So this suggests a very natural question. Does the notion of subtraction, does it categorify to the right column? So that's the next thing I want to speak about. And well, the answer is that there is a basically an insurmountable obstruction. So if you suppose X is an object in a category C, such that the coproduct of X with some other object Y is 0, or the initial object, then it's easy to see that that implies your object X must itself be the initial object. So I'll leave this as an exercise. It's not so hard. But the upshot of this is that there is no way to categorify subtraction or to add inverses with respect to the coproduct. Because again, any object which has an additive inverse with respect to the coproduct will automatically be initial. So that means like basically trying to categorify subtraction is a no-go. It won't be possible. There is a solution, broadly speaking, however, if we broaden what counts as success. So the solution goes as follows. A category has an underlying groupoid, and the idea is that we should categorify subtraction on this groupoid rather than on the level of the category itself. So let's illustrate this by an example. So if we consider again the category fin of finite sets and all functions between them, what does this category look like? There are objects for every finite set, and each of these has automorphisms given by the symmetric group, and there are additional functions in between them, which are not isomorphisms. So if you consider this category, well, you can restrict to the subcategory, which consists of all of the exact same objects, but now only the isomorphisms. So in that case, this is the green arrows, and you can take that subcategory, which is defined to be the underlying groupoid. So in general, say if you're working like this is a pretty mild operation. If you were working with, say, infinity categories modeled by quasi-categories, then you just take all the simplices whose edges are all isomorphisms. So you end up with an object that looks like this. In the case of finite sets, it's equivalently just the disjoint union of classifying spaces of the symmetric groups. Now, the observation is that the coproduct, which existed on finite sets, you can take the disjoint union of finite sets, well, it makes this groupoid into a commutative monoid. So for example, if you take a set with n elements and a set with m elements, well, you can take the disjoint union to get a set with n plus n elements. However, if you have, in addition, a symmetry of a set with n elements, along with a symmetry of a set with m elements, well, that gives a symmetry of the set with n plus m elements. So the coproduct on finite sets gives this space a commutative monoid structure, where now you can not only add objects, but it's also possible to add morphisms. And if you try like write down what it means to be a commutative monoid, well, you need a map from the product of this with itself back into itself, which will serve as multiplication. And it's given on connected components by this map, which is just induced by the inclusion of sigma n times sigma n into sigma n plus m. So the next goal, broadly, to make sense of what does it mean that we have a commutative monoid, which is a space. So classically, a commutative monoid, M, is a set M with a multiplication M, little m, which satisfies various conditions. So I'll write them as diagrams. So the first is that this multiplication, it should be unital. So there should exist some unit E for which the multiplication, the composition of the multiplication with the unit is just the identity. It should be associative, which means that if I multiply the first two coordinates here and then the result with the last coordinate, that should be the same as multiplying the last two coordinates and then the first coordinate. So it means that this square should commute. And then it also should be commutative. So the multiplication should commute with the map swapping the two coordinates. Then I wrote these conditions out in diagrams because now, well, the extension of this notion to spaces becomes clear. A commutative monoid in spaces should be a space M equipped with the multiplication, and now homotopies, which witness the fact that this multiplication is unital, associative, and commutative. So instead of asking for these diagrams to strictly commute, I merely am supplied with some homotopy between the two different compositions in the square. And in general, actually, you will need you need more and higher homotopies. For example, if you are multiplying together four different elements, well, there's various ways you can parenthesize them, and you need all the different ways which you could parenthesize the multiplication of four different elements to be suitably compatible. And those are encoded by higher homotopies between homotopies and so on. And just from the way I'm presenting it, it's not so clear how you might actually write down like what all this data is, but it turns out it is possible and it's not so hard to do. So for example, if M is a commutative monoid in spaces, then the connected components, which I denote by pi naught of M, is just a regular commutative monoid in sets. Now that we are equipped with the notion of a commutative monoid, we can make sense of what it means for a monoid to be a group. So a commutative monoid M is a commutative group if there exists an inverse map for the multiplication. And it turns out that, well, a commutative monoid being a commutative group is actually a condition. It's not additional data. So that means that the inclusion of the full subcategory of commutative groups, which I've denoted here by abelian group objects in spaces, into commutative monoids, it has a left adjoint, which is called the group completion. And the group completion is just the universal way to take a commutative monoid and turn it into a commutative group. So like the example is
What
that.
do you mean by the left one? Abelian groups like on space? What do you mean by the left one? This abelian
So
group? Or what?
this is I mean to say abelian group objects in the infinity category of spaces, which is just going to be commutative monoids which satisfy this condition that they are groups.
Okay.
Thank you for the question. So the example is that well, the group completion of the natural numbers is the integers, like as expected. So okay, so now that we have the notion of a commutative monoid and commutative groups and spaces, we are now equipped.
Another question. Sorry, this happen only by adding the homotopies condition, not the higher homotopies. Only the homotopy condition. If you back again, you add in only the or more higher homotopy you added to this category. What is the definition of this category?
So so a commutative monoid.
Sorry, for the commutative monoid as a space. Yeah, sorry.
Yeah, so a commutative monoid in the infinity category of spaces. So intuitively, it will consist of the data of a multiplication map, as well as a unit, such that these diagrams you are provided with. It will also include the data of homotopies witnessing the commutativity of these diagrams intuitively. But you also need like higher homotopies.
You need higher homotopy. You can define something only with homotopies, like something like only that using only homotopies. Like
yes, so
you can.
So you could do such a thing. You would arrive at the notion of like a commutative monoid in the homotopy category of the infinity category of spaces. But I mean here, like in classical language, to consider something which is called like an E infinity space. So
yeah. So you work on this when you mentioned later. So you mean this like with like one.
I mean this. I mean the fully homotopy coherence.
Okay.
Commutative monoid structure.
Okay. Yeah. Thank you.
I just meant to give the intuition here.
But, yes, I know, because it's maybe complicated to define it.
Right. But this is the idea, is that you have homotopies that witness commutativity and associativity, then higher homotopies which encode all the compatibilities. Okay. So but now that we have the notion of a commutative monoid and commutative groups in spaces, we are now able to categorify subtraction on the natural numbers. So the way that this goes is, well, you take the underlying groupoid of the category of finite sets, which again just looks like this disjoint union of classifying spaces, and take the group completion. And it turns out what you get is an object called the sphere spectrum, which I will come back to. So just to summarize, well, if you start with the category of finite sets, you can decategorify and remember only the isomorphism classes of finite sets, which gives you the natural numbers, and then group complete to obtain the integers. But we can do something more refined, which is to remember not only the isomorphism classes of the objects, but the isomorphism classes of the objects along with all the symmetries of those objects, the automorphism groups of those objects, which we consider now as a coherent commutative monoid in spaces. And then you can take the group completion of this coherent commutative monoid, and we end up with the sphere spectrum. So maybe this is a confusing point, so I'll stop here if anybody has any questions.
I have one. So the middle, no, sorry, the top thing when you group completion, was it the B of the sigma infinity?
This group completion?
The middle thing, is it?
Yes.
Yeah.
Is this B of sigma infinity?
Yeah, that's what
so sigma infinity, I suppose, is like the colimit of all the symmetric groups.
Yeah.
So this is not. This has it has a connected component for every integer, and that connected component is just B sigma n. You're asking if after, are you asking if after the group completion?
Yeah,
this is
maybe
also
maybe that this is like Z cross B sigma infinity or something. I don't know. Yeah, I'm asking after the group.
Yes, after the group completion, this should agree with the group completion of B sigma infinity, right?
Group completion of B sigma infinity.
This is not after the group completion. This is something called the sphere spectrum, and this actually is a space with non-zero homotopy groups, like arbitrarily high and arbitrary.
Exactly, plus finds. Oh yeah, so you have to take maybe the. Oh, I see. So you have to do something on the B sigma infinity further to get the higher. Okay.
Right.
Okay, thank you.
So again, just to summarize where we currently stand, we are trying to categorify subtraction, and we saw that it's not possible to categorify subtraction on a category, but you can consider the underlying groupoid of a category, and then group complete to categorify subtraction. So that's the story we have told so far. Okay, if there are no other questions, then I will continue. So this idea of categorifying subtraction very naturally led us to consider these homotopy coherent commutative groups, which are, again, spaces which are equipped with the multiplication, which is commutative, etc., coherently. And that is exactly the notion of spectra or connective spectra. So the slogan is that spectra are homotopy coherent abelian groups in spaces. So just like an abelian group is a set with some multiplication operation, spectra are spaces with a coherent multiplication. And it will be useful to consider an analogy with like classical algebra. So in classical algebra, you have like abelian groups. And in this higher algebra, which is the algebra of spectra, the central players are spectra. The unit in abelian groups is the integers, z. And in higher algebra, it is the sphere spectrum. And just like you can take the tensor product of abelian groups, there's also a tensor product of spectra, which make the category of spectra into a symmetric monoidal category. So that tensor product means that now you can suddenly start to talk about rings and modules and algebras in the world of spectra. And I'll make one more remark. A spectrum X, it has Z-graded homotopy groups. So a spectra, well, it has an underlying space, but it also has negative homotopy groups, which come from basically something analogous to the extension of like bounded below chain complexes to all chain complexes. So spectra are really like analogous to some sort of derived abelian groups, which are like chain complexes in abelian groups. Okay, so I want to give some examples to help clarify. Considering that spectra are homotopy coherent abelian groups, and abelian groups are very important in math, it's natural to expect that spectra appear in a wide variety of situations. And that is indeed the case. Classically, spectra, they represent cohomology theories. So, well, a cohomology theory of spaces, it has coefficients in an abelian group. And more generally, the so-called extraordinary cohomology theories, they have coefficients in spectra. And it's really the question of, well, what type of objects represent cohomology theories that led people to the first definitions of spectra. So in this language, we can consider some examples. You have the spectrum Z, which represents ordinary, like singular cohomology with integral coefficients. There is a spectrum called Ku, which represents topological complex K theory. So for example, the zeroth K theory group of a finite space X is just given by considering all complex vector bundles on X up to isomorphism. And then you have the operation of direct sum, and then you take the group completion. So that gives you an abelian group, which is a cohomological invariant of a space. And then another example is the sphere spectrum, which is the unit. And the sphere spectrum, it corresponds to the cohomology theory of stable homotopy or stable cohomotopy. So for example, the homotopy groups of the sphere spectrum are exactly the stable homotopy groups of spheres. So how do we study spectra? Well, in analogy with classical algebra, the hint will be to look at abelian groups. So if A is an ordinary abelian group, well, if it's finitely generated, then we have this like nice classification theorem. It's isomorphic to some free group of rank R, along with cyclic groups, along with the direct sum of cyclic groups of prime power order. And more generally, if A is not necessarily finitely generated, well, there is a fracture square, which basically means that you can break up A into the prime part and the rational part, along with the data of how these two parts glue together. So the rational part, of course, corresponds to in the finitely generated case to the free abelian group, and the prime part is these cyclic groups of prime power order. Now, formally, this fracture square is a pullback of the following form. You take the prime part consists of the completions of all primes, and the rational part consists of the rationalization. And then the gluing data is exactly the rationalization of the prime parts. Now, we should think of this decomposition of an abelian group as coming from an open-closed decomposition of sheaves on a space. So I'm working at like a particular prime now. If you consider like spec of the p local integers, well, there are 2 points. There's like a generic point of characteristic 0, which is here, and then a closed point of characteristic p. And an abelian group is like a sheaf on this space. And this decomposition of an abelian group into the prime part and the rational part, well, it corresponds exactly to some suitable notion of like completion of this sheaf or localization at these 2 points. So we can ask now the exactly analogous question in the chromatic case, in the topological case. So if we have now a homotopy coherent abelian group, how or spectra, how might we go about decomposing it? So we're led to consider the following picture. So it turns out in a precise sense, the spec of the sphere spectrum, again localized at a prime P, it looks like the following picture. So you have the classical points of Q, the generic point of characteristic 0, along with this closed point of characteristic P. But there suddenly appear in the world of spectra infinitely many intermediary characteristics that interpolate between classical characteristic 0 and classical characteristic P. And these are denoted by K1, K2, and by convention, basically Q, the rationals are denoted by K0 and FP is denoted by K infinity. So this picture of spectra is known as the chromatic perspective on stable homotopy theory. And the integer n is known as the height of the prime, Kn. Maybe I'll take a pause here. Are there any questions at this point?
I have one. So are these called the Morava K-theories or?
Yes. So there, in fact, exist spectra, which spectra Kn, which in a precise sense basically implement these primes. Yeah, these are exactly the Morava K-theories. Because spectra should be thought of as sheaves on this space. So the Morava K-theories are sheaves for which are supported exactly at these points.
So by a space here, what do you mean?
I mean that this is a space in the sense that the spectrum of a ring is a space.
Like you mean like S modules kind of thing, or?
Yes, you could think of S modules. I mean, so there's a very general procedure by which if you have, say, a symmetric monodal category, you can think about it as like sheaves on a scheme. And from purely the symmetric monodal category, you can recover, maybe it needs to be stable, you can recover the topological space of that scheme. So if you apply this procedure to the category of spectra, then this is the picture that you get. This is like the scheme for which the category of spectra behaves like quasi-coherent sheaves on it.
So do we also like this? I guess it was called the pullback. I don't know. We called it, I think, the fracture square or something. I think it's also called the Sullivan square or something, I guess.
Yes.
Is that like a similar? Because I mean, if you localize, I guess you get different information about the spaces, I guess, according to these different generalized cohomology theories. So is there like a square similar to that, which you can actually combine this local data into a
yes, that is exactly what happens. In theory, one can localize at each of these points and then try to put back the pieces together via what is known as the chromatic fracture square. It's exactly the same story. Yeah.
Okay, thank you.
Yeah. Okay, so I want to give some examples of different spectra, different cohomology theories, which lie at different heights in this picture. So height 0, which is it corresponds to like discrete abelian groups like Q, R, and C, basically abelian groups which are rational vector spaces. Height 1, it has objects like Ku, which is topological K theory. Also lying at height 1 is Ko, which is called real K theory. It's built out of the real vector bundles on a space. In height 2, there are objects like elliptic cohomology theories. And height infinity, well, it has like mod P singular cohomology. So chromatic height, it provides like a stratification of the stable homotopy category. And these are the spectra, the cohomology theories, which lie at each level. So one of the major players in chromatic homotopy theory is a construction called algebraic K-theory. So classically, algebraic K-theory is an invariant of a ring. So if you let R be a ring, then the zeroth K group is defined by taking the projective finitely generated R modules up to isomorphism under the operation of direct sum, and then the group completion. And this is like a algebraic analog of topological K-theory, because projective R modules, they're like algebraic vector bundles on spec of R. But it turns out, as we're used to now, instead of just taking isomorphism classes of projective R modules, you can just take the category of projective R modules and then pass to the underlying groupoid, and then take the group completion of this commutative monoid as like a coherent commutative monoid in spaces. And this will produce an abelian group, a commutative group in spaces, which is simply a spectrum, and it's called the K-theory spectrum of the ring R. And then the homotopy groups of this spectrum, they are like the higher K groups of the ring R. And algebraic K-theory is simultaneously ubiquitous, very important, and also extremely difficult to compute. So even the K-theory of the integers is not known entirely. These higher K-theory groups of Z, well, they are like related to very deep hard conjectures in number theory, as well as like manifold topology and diffeomorphism groups. They appear in a lot of different places, and they are like even this case is not fully understood. There are entire like books written about these higher K-theory groups. Now, one of the reasons why algebraic K-theory appears in chromatic homotopy theory is because of a phenomenon which is known as redshift. So it turns out that Ku, which was topological K-theory, and it lies in height 1, it is basically equal to, say, after a P completion, the algebraic K-theory of the complex numbers C. And the key observation here is that the complex numbers is a spectrum of height 0, and Ku is a spectrum of height 1. And by applying algebraic K-theory to something of height 0, we obtain something in height 1. So Osoni and Rognes in the 2000s, they computed the algebraic K-theory of Ku, which is a spectrum of height 1, and they found that it lies in height 2. So to summarize, well, from the complex numbers in height 0, by applying algebraic K-theory, one lands in height 1. And then by applying algebraic K-theory again, you land in height 2. So based on this computational evidence, they made a series of conjectures, which are collectively known as the redshift conjectures, and say, like, more or less, that algebraic K-theory increases chromatic height. And there are various more qualitative formulations of these. And recently, in the past five years, a tremendous amount of progress has been made on these conjectures.
Question.
Yes. Yes, of course.
Does this also mean that when we do the K of Kn, we get Kn plus 1? Is this known?
So I do not think I think this is I think the algebraic K-theory of Morava K-theories is I've just recently heard something about results in this direction, but I do not know off the top of my head if this case is known. Very recently, like the algebraic K-theory, the redshift conjectures were proven for any like E infinity ring, like a fully coherent commutative ring in spectra. But the Morava K-theories are not. They are like E1 rings at the most. So I think these cases are still open.
Okay, thank you.
So I want to remark that in the construction of the K-theory spectrum, well, we take from a ring R, we pass to the category of R modules, and then a group completion, and then take group completion. So the K-theory is constructed in two steps. There's a passage to modules over R, and then a group completion. And in a precise sense, well, the redshift happens in the passage from the ring R to the category of modules over R. And that suggests a more general redshift philosophy, which is perhaps developed by Carmeli Shankinovsky and others. And it says that categorification increases height. So algebraic K-theory is an instance of categorification, but philosophically, the step of categorification is what is resulting in the increase in chromatic height. And this philosophy, I mean, it's seen some like major applications in like the past few years, and in my mind has like a lot of potential for shedding light on very deep structural properties and structural phenomena that appear in chromatic homotopy theory. I'm pausing. I want to pause for any questions. Okay, so if there are no questions, then
Actually, I have one. So
yes.
I guess you gave the simplest example of the construction where the shift happens. I think this is the most familiar example going from C to KU. What is the next one? Like next complicated case? If you did you say if you do KKU, is it known or?
Yes, so this was the
no. This is computer. Okay, that's the
this
next.
is one of the computations which led to the conjectures, and various variations on this computation, like KU mod P or different. Yes. Okay, so I want to make I want to speak about two more things before I conclude. The first is to explain the terminology redshift. And then the second is to describe some of the questions that I've been thinking about. So chromatic homotopy theory, well, it began somewhat computationally with the question of computing stable homotopy groups of spheres. So this chart right here is something called, well, it's a picture of the atom spectral sequence, which is a computational tool for determining stable homotopy groups of spheres. And if you have not seen a spectral sequence before, or this spectral sequence, it's totally okay. The picture is just that each one of these dots here corresponds roughly to an element in stable homotopy groups of spheres. So each of the columns here corresponds to a certain degree in stable homotopy groups. And then the lines connecting them indicate the relationship between these different elements. But when you look at this picture, it's there's like it's not clear what's going on. However, there are some patterns. For example, you have this triangle which appears basically every 8 degrees. And chromatic homotopy theory is about the hope that this picture, which when you look at it all at once, is very complicated. But it's possible in theory, it might be possible in theory to decompose all of this picture into various layers or frequencies, which by themselves individually exhibit periodic behavior. So this eightfold periodicity is exactly corresponds to the height 1 chromatic layer, and it was like originally detected via the J homomorphism. And then higher chromatic layers, well, they correspond to different families of periodic elements in the stable homotopy groups of spheres. And as you increase the height, the chromatic height, the period increases. So like the wavelength increases, and thus the passage from height n to height n plus 1 is referred to as redshift.
So does that mean we are not going to see much pattern if you just look at small dimensions for the different colors than blue?
Yes, so even in height 2 already, the periodicity is of like order 256, some like pretty large number. And then even beyond height 2, it's like computations become like almost impossible to do. There isn't in theory like computations become like prohibitively difficult even above like height 2. But this is in theory the picture which should emerge. So I want to conclude by briefly describing some of the questions that I like to think about. Given a cohomology theory, given a spectrum as a cohomology theory, we can ask a very concrete question. What are the associated cohomology operations? So these are like natural operations on the cohomology of your space. So for example, if you're working in F2 cohomology, you have the action of the Steiner algebra. On topological K-theory, there are the Adams operations. And it turns out in rational cohomology, there are not that many operations. You can just take a single element and raise it to the ith power. And the point is that these cohomology operations, they're important. If you remember like the FP cohomology of a space along with its structure as a module over the Steiner algebra, then you have some hope of saying something about its homotopy type. Or even the existence of Adams operations in topological K-theory gives like a very easy proof of the Hopf invariant 1 problem. So these are important. And so this is somehow like a very concrete question you can ask about a spectrum. What are its power operations? What are the natural operations which act on it viewed as a cohomology theory? So I'll give you an example of a result in this direction. So a lambda ring is a commutative ring R equipped with operations lambda n. And the idea is that these should behave like exterior powers, like some decategorified version of an exterior power. So there should be some identities which govern the behavior of these operations on sums, on products, and their compositions. And important examples include like the collection of vector bundles on a space. You can take like the exterior power of a vector bundle, and similarly the representation ring of a group G. Then I mean, something to observe here is that all of these examples, they arise as like they arise via categorification. You have some category of vector bundles or category of representations, and the passage to isomorphism classes, it obtains the structure of a lambda ring. So a result in this direction is if you let C be any infinity category of height 1, and it needs to be orientable, which means something, which I won't currently define, then commutative algebras in C, they have exactly the power operations of a p-typical lambda ring. So this should be considered an instance of the redshift philosophy, because it's saying that the type of power operation structure which appears in the categorified context of vector bundles and representation rings, for example, is exactly the power operations which appear in height 1, which you should think about as coming from categorifying height 0. So I think I will stop here. Are there any questions?
Thank you very much, Beckham. Yes, please, questions for Beckham.
No, really, it's a good idea. Thank you very much, Beckham.
Okay, maybe I can ask a bit more if you could unravel the your theorem. So I see p-typical here. Does it mean in the sense of some sort of a p-typical lambda ring here? Is it should I think of like a what was that called, like a group law or something?
So
what is
so
it?
the reason, yes, so the reason why the reason why this p-typical is appearing here. Okay, first, what does it mean? P-typical means that you can repackage the structure of a lambda ring into an equivalent structure where you supply something called a p derivation for every prime. So there is a natural sense in which the structure of a lambda ring breaks up into different prime structures for each prime with some compatibility condition. So p-typical lambda ring.
May I ask something? Maybe that would help me to understand. But is it connected to the equivalence theorem on the Lazard ring, or somehow?
This equivalence theorem on the Lazard ring begins the entire story of chromatic homotopy theory. But this appearance of p-typical. It's
too long to take it from there, but maybe connecting it to there could be helpful somehow. Because the okay, I don't know. You didn't describe the Moravec theories as coming somehow from the cobordism ring, cobordism theory, but somehow they're connected, right? Maybe
yes.
you get exactly the Moravec in one step, but you get them in a couple of steps. So that's why I was kind of thinking it would be nice to maybe just quickly, if that's possible. I mean, that would be quite helpful to put your theory into context. Yeah.
So I don't think the appearance of p-typical lambda ring in this theorem is directly related to formal groups and formal group laws. But I can say in general that the construction of the chromatic picture originally came from like the algebraic geometry of formal groups, the formal group laws, which is something I didn't mention at all. But the hope, I think the hope in the story that I'm trying to tell is that there is a perspective of chromatic homotopy theory which is independent of like formal groups. It's coming from categorification. I meant to think about categorification.
So when you say orientable infinity category of height 1, I mean, this is like a big jump from the lambda rings that you gave over there, which are very classical, just goes back to the work of Attia. So how should we think about them more? I mean, the jump from examples to the theorem is a bit too much, maybe. I mean, since we have a bit more time, maybe you can say, if you like, how should we think about orientable infinity categories of height 1?
That's a very good question. So the word orientable here, it implies the existence of something which we should think about as a splitting principle. So again, in like the whole theory of lambda rings on K theory, the splitting principle, it plays like a very important role. It kind of like allows you to reduce any question you have about vector bundles into questions about line bundles. And then something you want to show about lambda rings, you can just formally reduce to the case of line bundles. So this orientability condition, you should think about it as in height 1, providing the analogy of a splitting principle, which reduces like questions about say arbitrary vector bundles into questions about line bundles. That's how I would try to summarize.
Okay, thank you very much. So any other questions before we thank Beckham again? Any other questions?
No.
Aziz, are you okay? Sorry, I thought you.
No. I want to thank Beckham for this. Yeah, really interesting thing. Yeah, really. We enjoyed it.
Yeah, then let's thank Beckham again. Thank you very much.